Hello friends, I welcome you in lecture number 7 on residue integration of real integrals. We have discussed 6 lectures on this topic, and in earlier 6 lectures we have seen that suppose we have improper integral from minus infinity to infinity fx dx, then if we want to find out principal value of this improper integral, then if our function fx is a rational function such that this degree of q is strictly greater than 1 plus degree of p, and this qx is non-zero for every x belongs to R, then this principal value is given by 2 pi I times sum of residues of corresponding complex function f of z at poles in the upper half plane. So this is the formula which we are using from last several lectures. So to use this formula, we have this assumption that fx is a rational function, degree of q is strictly greater than 1 plus degree of p, and qx is non-zero for every x belongs to R. That is, there are no zeros of qx on the real axis. And that means if we consider the corresponding complex function, say f of z equal to p of z over q of z, then this condition implies that this q is also non-zero on the real axis. That is, qz has no zeros on the real axis, and because this f is a rational function, since qz is non-zero on the real axis, we can say that f of z has no poles on the real axis. So in evaluating this principal value, we have assumption that this function, complex function f of z, has no poles on the real axis. But sometimes what happens that your complex function fx is such that if you consider the corresponding function f of z, then sometimes f of z may have poles on the real axis. So in that case, how to find out Cauchy principal value of this improper integral? So for that we have another formula. So for that what we can do is, first we write down the corresponding complex function and we find out the values of z for which qz equal to 0, which are on the real axis. Or we first find out all the zeros of qz, and then we find out which zeros are on the real axis and which zeros are in the upper half plane. So we find out poles of f of z which are on the real axis, as well as we find out poles which are above the real axis or which are in the upper half plane. After that, principal value is given by 2 pi I times sigma residue of f of z plus pi I times sigma residue of f of z. Now this first summation is residue of f of z at all the poles in the upper half plane, and this second summation is residue of f of z at all the poles on the real axis. So if our complex function f of z has poles on the real axis, then we have to add this summation in the previous formula. In previous formula we are using this formula only because we have assumed that given function f of z has no poles on the real axis. But if f of z has poles on the real axis, then we have to add this summation. So this first summation extends over all the poles of f of z in the upper half plane, and second summation extends over all the poles on the real axis. So with this in mind, we can do this example number 6 in today's session. So for that we have written this result, that how to find out improper integrals or how to find out Cauchy principal value of improper integral in the case when poles are on the real axis. So suppose our complex function f of z equal to p by q has simple poles on the real axis, then Cauchy principal value of this improper integral is equal to 2 pi I times summation of residues of f of z at all the simple poles in the upper half plane plus pi I times summation residue of f of z at all the poles on the real axis. Okay, so here we have written this first sum extends over all poles in the upper half plane, and this second sum extends over all poles on the real axis. So with this formula we try to evaluate Cauchy principal value of this improper integral. So first we write down given function. So our function f(x) here in this example is 1 divided by x square minus 3x plus 2 into x square plus 1. X square minus 3x plus 2 times x square plus 1. So first we consider the corresponding complex function. Let f of z is 1 over z square minus 3z plus 2 times z square plus 1, and if we compare with p by q, suppose this is equal to p by q, then denominator polynomial is qz, which is equal to z square minus 3z plus 2 into z square plus 1. So we find out values of z for which qz equal to 0. So we solve this qz equal to 0, that means this product is 0, that means z square minus 3z plus 2 equal to 0 and z square plus 1 equal to 0. Okay, this we can factorize by rewriting this minus 3z as minus 2z minus z plus 2, and this is z square equal to minus 1, that we will replace by I square, and here we have this z common from this, here we can take minus 1 common, here we write this as z square equal to I square, and if we take z minus 2 common here, we have z minus 2 into z minus 1 equal to 0, and if we consider this one z square equal to I square, then z has two possible values, I and minus I. So the possible values of z are z equal to 1, 2, I and minus I. So we can observe that this z equal to 1 and 2 are on the real axis. Suppose this distance is 1, then z is 1, 2, I will be somewhere here and minus I is here. So I is in the upper half plane, 1 and 2 are on the real axis, and minus I is in the lower half plane. So we ignore minus I because it is in lower half plane. And because f of z is a rational function, we can see that this z equal to 1, 2 and I are poles of f of z. Okay, so and they are simple poles. So f of z has simple poles at z equal to 1, 2, I. We are not writing minus I, it is also a simple pole, but it is in lower half plane, so we ignore that z equal to minus I. So among which z equal to 1, 2 are on the real axis and z equal to I is in upper half plane. that is, it is above real axis. So now we calculate residues of f of z at all these three simple poles. First we calculate at z equal to 1. So first we write our function f of z is 1 over z square minus 3z plus 2 times z square plus 1, and because this z equal to 1 and 2 are roots of this polynomial can be written as product of two linear factors z minus 1 into z minus 2, and we keep this z square plus 1 as it is. Now here to find out residue, we are using this result. We will try to express f of z as phi of z over z minus 1, where phi of z is analytic at z equal to 1 and value of phi at z equal to 1 is non-zero. So for that we keep this z minus 1 in the denominator and we consider this remaining part in the numerator. So z minus 2 times z square plus 1. So this is our function phi. So it is clear that this function phi in the numerator is analytic at z equal to 1. Phi of z is a rational function. It is not analytic at points where z minus 2 and z square plus 1 are 0. So this is, I have to write only z minus 1, phi of z over z minus 1, where this phi of z is 1 over z minus 2 times z square plus 1. It is analytic at z equal to 1, and value of phi at z equal to 1 must be non-zero, so that we check by taking z equal to 1 here. So here if I put z equal to 1, I have 1 minus 2 minus 1, and this is going to be 1 plus 1 2, so this is minus 1 half, so it is non-zero. And here power of z minus 1 is 1, so we are able to express f of z as phi of z over first power of z minus 1, where phi of z is analytic at z equal to 1 and phi of 1 is non-zero. So this says that f of z has a simple pole at z equal to 1. F of z has a simple pole at z equal to 1, and residue of f of z at z equal to 1 will be equal to value of function phi at z equal to 1, which is minus 1 by 2. Similarly, we calculate residue at z equal to 2. So in this case, we keep z minus 2 in the denominator. Okay, we keep z minus 2 in the denominator and we consider remaining portion, this we will consider in the numerator. So we write f of z as, because we are interested at z equal to 2, we keep z minus 2 in the denominator and z minus 1 and z square plus 1 in the numerator. So in this case, this is our function phi, here z minus 2, where this phi of z is 1 over z minus 1 times z square plus 1. So this is clearly analytic at z equal to 2, because it is a rational function, and at z equal to 2 this denominator remains non-zero. So phi of z is analytic at z equal to 2, and value of phi at z equal to 2 is 1 divided by, we put z equal to 2 here, so 2 minus 1. If we put z equal to 2 here, we have 2 square, that is 4 plus 1, which is 5. So it is 1 by 5 and it is non-zero. So f of z is written as phi of z over z minus 2 to the power 1 where phi of z is analytic at z equal to 2 and phi of 2 is non-zero. Therefore f of z has a pole of order 1 or a simple pole at z equal to 2, and residue of f of z at z equal to 2 is nothing but value of function phi at z equal to 2, which is 1 by 5. So we have obtained residue of f of z at poles on the real axis. Now we calculate residue of f of z at pole in the upper half plane, which is z equal to I. So now we try to calculate residue of f of z at z equal to I. So for that we require z minus I in the denominator. So we consider first our function is z square minus 3z plus 2 times z square plus 1. So now I can write z square plus 1 as z square minus minus 1, and I replace minus 1 by I square. So therefore f of z is 1 over z square minus 3z plus 2 times z square minus I square can be written as z minus I into z plus I. Now we are interested in the residue at z equal to I, so we keep z minus I in the denominator and we consider all other things in the numerator. So we are rewriting f of z in this way. This is z square minus 3z plus 2 times z plus I. So in this case our function phi is phi of z over z minus I, where now this phi of z is 1 over z square minus 3z plus 2 times z plus I. Now this denominator is non-zero at z equal to I, so phi of z is analytic at z equal to I, because phi of z is a rational function at z equal to I, and here also we have to find out value of function phi at z equal to I. So we put z equal to I here, I square minus 3I plus 2, and here I plus I, that is 2I. Now if we consider I square equal to minus 1, we have minus 1 minus 3I plus 2 into 2I. Okay, we replace I square by minus 1, so minus 1 minus 3I plus 2. Again this can be rewritten as 2 minus 1, that is 1 minus 3I into 2I. So we can keep this 1 over 2I as it is. This is 1 minus 3I, and we can multiply numerator and denominator by 1 plus 3I. To simplify this, we have 1 minus 3I is multiplied with 1 plus 3I. So we are multiplying numerator and denominator by conjugate of 1 minus 3I, which is 1 plus 3I, and we keep this as it is. So this is going to be 1 minus 9I square, and here we have 1 plus 3I. So this is going to be 1 over 2I, this is 1 plus 3I, because I square is minus 1, this is going to be plus 9, and 1 plus 9 is 10. And we can replace 1 over I by minus I, so we have minus I into 1 plus 3I, and here we have 2 into 10, that is 20. So I can take multiplication by minus I here, or I can multiply with I, so I have I plus 3I square, and because I square is minus 1, we have I minus 1, I minus 3. If we put I square equal to minus 1, I minus 3 divided by 20, and if we take negative sign inside, we have 3 minus I divided by 20, which is non-zero. So value of phi at I is non-zero, which is 3 minus I over 20, and phi is analytic at z equal to I, and f of z is written as phi of z over z minus I to the power 1. So therefore f of z has a simple pole at z equal to I, also has a simple pole at z equal to I, and residue of f of z at z equal to I will be equal to value of function phi at I, which is nothing but 3 minus I divided by 20. So we have obtained residue at all these three simple poles 1, 2 and I. So now we can apply that formula. So now the Cauchy principal value of given improper integral value is, first we write the formula. Cauchy principal value is equal to minus infinity to infinity fx dx will be equal to 2 pi I times sum of residues of f of z in the upper half plane. So here there is only one simple pole in the upper half plane, which is z equal to I. So here we multiply residue of f of z at z equal to I, because z equal to I is in the upper half plane, plus pi I times sum of residues of f of z at poles on the real axis. So there are two poles on the real axis, z equal to 1 and z equal to 2. So here we consider sum of residues of f of z at z equal to 1 and 2. Okay, so this first summation is residues of f of z at simple poles in the upper half plane, and this is sum of residues of f of z at simple poles on the real axis. So now we substitute all these values. 2 pi I times residue of f of z at z equal to I is this one, 3 minus I over 20. So here we write 3 minus I divided by 20 plus pi I times residue of f of z at z equal to 1 and z equal to 2. So at z equal to 2 it is 1 by 5, and z equal to 1 it is minus 1 by 2. So minus 1 by 2 plus 1 by 5. Residue at z equal to 1 is minus 1 by 2, at z equal to 2 it is 1 by 5. So here we can cancel out 2, and here we have 10, and we can take pi I common, which is there in both the terms. So pi I common, and here we have 3 minus I divided by 10. Pi I is taken common, here 2 is cancelled out, and here we can take 10 LCM. So we have minus 5 plus 2. So now we simplify this. Pi I divided by 10, this is going to be 3 minus I, and this is going to be minus 3. So pi I divided by 10, 3 will cancel out, minus I. So we have minus pi into I square divided by 10, and if we use I square equal to minus 1, we have pi by 10. So therefore Cauchy principal value of given improper integral, now we replace fx by given function, it is x square minus 3x plus 2 times x square plus 1. So Cauchy principal value is pi divided by 10. So if your function has poles on the real axis, then you have to calculate residue of f of z at poles on the real axis as well as poles on the upper half plane. Then this summation of residues of f of z at poles on the upper half plane is multiplied by 2 pi I, and summation of residues of f of z at poles on the real axis is multiplied by pi into I, and we obtain Cauchy principal value. Okay, so this is all about this lecture. For this lecture, what is special thing is we have considered improper integral, in which our function f of z has simple poles on the real axis. And in earlier lectures we have considered those functions for which there are no poles on the real axis. So if your function has simple poles on the real axis, then in the formula for Cauchy principal value we have this extra summation pi I times residue of f of z at poles on the real axis. We have to add, or we have to write down summation of residues of f of z at simple poles on the real axis, and this summation is multiplied with pi into I. This summation is multiplied into with 2 pi I. So this is all about this lecture. I hope you like it. Thank you very much.